Hey guys, how's it going? In today's video, I'm going to be showing you how to set up the PZEM-004T version 3 current sensor with the Raspberry Pi. Before we get started here, I just want to make a disclaimer that we will be working with mains voltage, so definitely proceed at your own risk, and I am not liable if you get electrocuted or if your house catches on fire. As always, you can find the links to all the components in the description below, and I'll also post the link to my website, which will have the official write-up. So let's quickly discuss all the components that you'll need to follow along in this tutorial. So right off the bat, you're going to need a Raspberry Pi. In this case, I'm using Raspberry Pi 4. You need a PZEM-004T version 3 kit. So what's usually provided in the kit is a coil, a USB to TTL converter, and the sensor and housing. I want to make a quick note about the provided USB to TTL converter. When I tried to use it with the Pi, I was getting a response length invalid 0 error, and apparently this was due to the poor quality of the provided USB to TTL converter. So the solution that I found that works is to use a different USB to TTL converter, which is displayed on the right. So I highly recommend that you use a third-party USB to TTL converter. So moving on to the wiring harness, you're going to need a 3-wire power cord and a hinged cord outlet. So I'm based in the US, so I'm using the US standard, and I picked this up at my Home Depot, so you can find this at any hardware store. If you're based abroad and using 220 volt or a different outlet standard, you're going to have to modify your cable wiring harness setup a little bit. And then also on the top left, I'm using DC electrical wire, and it's much better to use lamp cord because the insulation is better, and it's rated for mains voltage. I just didn't have any in hand, so that's what I'll be using in this tutorial, but definitely use lamp cord if you can, and I'll have that link in the description. So the first thing that we need to do is set up our wiring harness. So you need to take out your 3-wire cord and look at the stripped end. Usually they're color coded. Green is ground, white is neutral, and then black is hot. But in this case, I don't have the color codes. The left is hot, the middle is ground, and the right is designated neutral because there's 3 ridges on it. Moving on to the hinged outlet, if we inspect the internals, we can see on the left side the brass colored screw is for the hot line, and then the green screw on the bottom is for ground, and then the silver one on the right is for neutral. So now that you've identified where all the leads go to, you need to take your 3-wire cord and strip the ends a little bit more so you have an inch or so to work with. And then you're going to take maybe 5 inches of lamp cord and attach the hot side to the hot wire and solder that to the end, and then take the neutral side on the right and then also solder it on the end, so that way it looks something like this. Here's a closer look at how your wiring harness should look after you finish soldering both wires. So now you're ready to finalize your wiring setup. You're going to take the AC coil and slip it over the hot line and then attach the hot line to the brass screw on the left. Take your ground wire and attach it to the green screw on the bottom, and then take your neutral wire and attach it to the silver screw on the right. Here's another angle of what it should look like. So once this is done, you can clamp down the hinged outlet and attach the screw to ensure everything is secured in place, and you should be good to go. The end product should look similar to this. So now we're ready to attach the wire leads to the screw terminal on the sensor. So just to make a note of the orientation here, the PZEM sensor screw terminal is on the right side. So starting with the coil, we're going to take the positive wire and screw it into the bottommost terminal, and then take the neutral wire and then screw it into the one right above it. And then for the lines that we've tapped on the 3-wire cord, we're going to take the positive hot wire and attach it to the second screw terminal from the top, and then take the neutral wire and attach it to the top screw terminal. And that should complete the physical wiring setup from the harness to the sensor. So all that's left of the physical setup is to wire up the USB to TTL converter to the sensor. So it may be hard for you to follow along, so I'll throw up a schematic. On the USB dongle side, we're not going to use the 3.3 volt pin. We're just going to match the 5 volt pin to the 5 volt pin on the sensor. And then for the TX on the dongle, we're going to match it to the RX on the sensor. And then for the RX on the dongle, we're going to match it with the TX on the sensor. And then we're just going to match ground to ground. And that completes the wiring setup for the USB to TTL converter, and then you can just plug the USB side into the USB 2.0 port on the Raspberry Pi. So once that's complete, you can boot up the Pi, and then we have to set up a few things in the OS. So let's head over to the terminal. Okay, so I've SSH into my Raspberry Pi. If you're using the GUI, you can just open up a terminal and follow along. It'll be the exact same process. So before we start typing commands, we just need to ensure that you have everything hooked up correctly. Your wiring harness, the opposite end with the coil should be plugged into the wall, and the USB to TTL converter should be plugged into your Raspberry Pi. Once you ensure all those connections are made and the Pi is successfully booted, you need to check to see if the serial interface is active. So we're going to type sudo raspi-config, and then we're going to navigate to the interfacing options and go down to the serial, and we're going to set this to no, and we are going to activate the serial port hardware. Hit OK. And once that's done, it may require you to reboot. So just hit yes and wait for it to reboot. Okay, so I just successfully rebooted and we're back up and running. So let me just do some cleanup here. So the next thing that we need to do is identify the USB serial device has been detected by the Raspberry Pi. So we're going to type this command dmessage space pipe space grep tty, and you should see something like this on the bottom line. PL2303 converter now attached to TTY USB 0. So you want to make note of this path, TTY USB 0. So that's good. So the next thing we need to do is install the Python library. So we're going to type sudo pip3 install modbus-tk and then hit enter. So now we should be good to go to run the Python script. So let me just do some cleanup real quick. Yeah, so if you go to the description below and navigate to my website, you can retrieve the code. I've already done that. So I've created this script PZEM-004T. So let's just inspect that real quick. Sudo nano PZEM. And basically, if we go to line 11, we can see that the correct path has been defined to the USB to TTL converter. So I'll quickly run through this code right now. So on the top 6 lines, we're importing our necessary libraries. We have our main block, and then line 10 through 17, we're just defining the serial interface, and then here on 19 is where we're activating the connection to the PZEM device, and it's using the RTU protocol. There's some other parameters set here, and then 24 we're setting this empty dictionary so that way we can build our payload. And on line 26 we start the infinite loop, and on 27 we're reading the input registers, and 29 through 36 we're building our dictionary payload. So we're taking the input register data and then appending it to this dictionary, and then we're just printing it out here. Once the dictionary is built, you can do whatever you want with it. Either you can print it out like I'm doing here, or you can pass it along to an API or log it or whatever. And then finally on line 42 we have some error handling just in case we experience issues with exiting the script or there's problems. So keyboard interrupt, if we hit Control C, it'll exit gracefully. And then line 44, this just catches any other exceptions you may encounter. And then I have a finally clause here to close the connection with the device no matter what happens. So that's basically how the script works, and we should be good to go from there. So let's just close this out, clear the screen, and we can run the script. So just a quick note, there's nothing plugged into the wiring harness currently. I'm just going to run the script to see if the sensor is working properly. So we're going to type Python 3 PZEM.py, and we should see some dictionary output. All right, cool. So it's working. So at this point, I'm going to kill the script and we're going to run some tests to validate the accuracy a bit. Let me just clear the screen here. So to go over my benchmarking process, I've taken a soldering iron and hooked it up to a kilowatt and recorded all the results. And now I'm going to hook up the same soldering iron to the PZEM sensor, and then we can compare the results. Here's a photo of how it's currently set up. So let's go ahead and run the script and see how it performs. Okay, we're just gonna give it a quick second so we can get some values here. And I'm gonna stop it now. Okay, let's just scroll up and see. Okay, so let me throw up the values I got from my kilowatt, and then we can compare it to some of the results we see here. So from the kilowatt, I'm getting about 121.8 volts, and we can see here it's 121.5 to 121.7, so pretty close there. Amperage wise, we're seeing quite a bit of variance. Was it 0.42, 0.139, 129, 121, and then on the kilowatt I'm getting 0.29. So yeah, it looks like it's slightly off there. And then wattage, 52, 14.8, 12.9, 13.1. I'm getting 14.7 steady on the kilowatt, and then frequency 60 hertz. That's pretty standard. That seems accurate. So yeah, you can see that the PZEM's pretty variable. Let's run this again and just see if this is the case all around. So yeah, I think with what we can deduce from these test results is that it's not going to be super accurate, but it should give you somewhat of an estimation of how much power you're using. I'm pretty sure there's a way to calibrate the sensor, but it's not really clear to me, like going through the documentation and working with the RTU protocol. But if you guys figure it out, definitely leave a comment down below. And that kind of concludes the tutorial for today. I hope you learned a lot on using this PZEM sensor. It's been pretty tricky for me to get working, but yeah, guys, definitely leave a like and subscribe and stay tuned for upcoming content. Peace.